The machine weighed more than 24,000 tons. Not the mountain it was digging through, the machine itself, a moving mass of iron, steam, gears, cables, and steel, large enough to swallow entire buildings beneath its shadow. When it moved, the ground shook. When it stopped, production stopped with it. And when it broke, thousands of workers waited while entire industrial schedules collapsed around a single piece of machinery. To the men who worked near it, it did not feel like equipment. It felt like a force of nature that had somehow been built by human hands. The late 19th and early 20th centuries were an age of appetite. America needed coal. It needed iron ore. It needed stone. It needed the raw materials required to build railroads, bridges, factories, cities, and eventually an industrial empire stretching from coast to coast. But there was a problem. The richest deposits were often buried beneath mountains of earth and rock, and human labor alone could not remove them fast enough. The demand for material was growing faster than men with picks, shovels, and explosives could supply it. Industry needed something larger, something stronger, something capable of eating entire landscapes. The answer arrived in the form of giant excavating machines, whose size bordered on the absurd. Machines so large that railways had to be built simply to support them. Machines that could remove more earth in a day than hundreds of workers could move in weeks. Machines that transformed hills into pits and mountains into empty space. They helped build modern America. They also consumed workers, landscapes, towns, and fortunes along the way. Because every industrial miracle hides a contradiction. The machine that solved one problem often created another, and few machines embodied that contradiction more completely than the giant iron colossi that reshaped the American continent. The question is not how these monsters worked. The question is what kind of world became so hungry that it needed machines capable of devouring mountains. Welcome to History Forged. This channel explores the rise of industry, the evolution of engineering, and the people who worked inside the world's most powerful machines. We cover steel production, railways, infrastructure, industrial disasters, manufacturing systems, and the technologies that transformed civilization. If that sounds interesting, subscribe and join us for more industrial history and engineering documentaries. Long before giant excavators began carving entire hillsides apart, the industrial world faced a problem that seemed impossible to solve through human labor alone. The problem was not a lack of resources, it was access. America possessed enormous reserves of coal, iron ore, limestone, copper, and other materials essential to industrial growth. The challenge was extracting them at a speed that matched demand. During the 19th century, industrial expansion accelerated faster than almost anyone anticipated. Railroads stretched across the continent, steel mills multiplied, cities expanded upward and outward, factories consumed raw materials in quantities that would have seemed unimaginable only decades earlier. Every mile of railroad track required iron and steel. Every bridge demanded stone and metal. Every factory required fuel. Every growing city depended on a constant flow of construction materials. The industrial system had become hungry, and its appetite increased every year. At first, the solution was simple. Use more workers. Mining operations relied heavily on manual labor. Men with picks loosened rock. Shovel crews loaded carts. Horse-drawn wagons transported material. Explosives fractured larger formations. The process was physically exhausting, dangerous, and painfully slow. Yet for a time, it was enough. Industrial demand remained within the limits of what human labor could provide. Then those limits began to break. As surface deposits became depleted, mining companies were forced to pursue larger and more difficult reserves. The easiest resources had already been taken. What remained often lay beneath enormous layers of earth and rock, where entire hills had to be removed before valuable material could even be reached. This created a bottleneck that traditional methods could not overcome. A worker with a shovel could move only so much earth in a day. A horse could haul only so much weight. Even explosives had limits. Blasting fractured material, but the debris still had to be removed. Every ton of earth represented labor. Every additional foot of overburden required more workers, more animals, more time, and more money. Industrial demand continued rising. Productivity did not. The imbalance became increasingly severe. Mining companies found themselves trapped between abundance and scarcity. The resources existed. The means to access them efficiently did not. This contradiction appeared most clearly in large open-pit mining operations. Now, some ore deposits were buried beneath hundreds of feet of worthless material. Removing that material became the dominant task, not mining the resource itself. The earth above the deposit often weighed far more than the ore beneath it. Companies were effectively spending enormous amounts of labor simply to reach the thing they actually wanted. And labor was expensive, not merely in wages, in housing, transportation, food, medical care, equipment, supervision. Every worker represented a cost that extended beyond the shovel in his hands. Adding more labor solved problems only temporarily. Eventually, scale overwhelmed manpower. The mathematics became impossible. A project requiring 10,000 workers today might require 20,000 tomorrow, then 30,000, then 40,000. Industrial growth was beginning to outpace the capacity of traditional extraction methods. Meanwhile, competition intensified. Steel companies competed for ore. Railroads competed for fuel. Construction firms competed for stone. Entire industries depended on resource flows that were becoming increasingly difficult to maintain. Shortages disrupted production. Production delays affected profits. Profits influenced investment. The consequences rippled outward through the economy. What appeared to be a mining problem was actually an infrastructure problem. The industrial system itself was becoming constrained. This pressure created demand for a new kind of machine. Not merely a better tool, not merely a larger shovel, something fundamentally different. A machine capable of replacing hundreds of workers simultaneously. A machine that could convert fuel into excavation on a scale previously impossible. Engineers had already begun experimenting with steam-powered digging equipment. Early steam shovels demonstrated the basic concept. Instead of relying on human muscle, they used boilers, pistons, gears, and cables to generate force. These machines could move more material than traditional labor crews, but they remained limited. They were large by contemporary standards, yet small compared to the challenges emerging in major mining regions. Industrial demand continued expanding, and so did the required scale of excavation. The problem was no longer measured in wagon loads. It was measured in landscapes. Entire ridges needed removal. Valleys required reshaping. Mining companies began looking at mountains not as geological features, but as obstacles standing between industry and raw material. To remove a mountain manually was absurd. To remove it mechanically began to seem necessary. This shift in perspective was profound. For most of human history, geography imposed limits. Mountains dictated routes. Rivers determined settlement. Terrain constrained ambition. Industrial society increasingly rejected those limitations. If a mountain blocked access to resources, the mountain itself became expendable. The challenge was building a machine large enough to make that philosophy practical. Such a machine would require unprecedented engineering, massive structural frames, power systems capable of sustained operation, excavation mechanisms strong enough to tear through rock and earth continuously, transportation systems capable of moving extraordinary quantities of material, and perhaps most importantly, a workforce capable of operating and maintaining equipment unlike anything previously seen. The industrial world was moving toward a new relationship with the landscape, one in which geography would no longer be accepted as fixed. Instead, it would be treated as raw material, something to be reshaped, relocated, or removed entirely. The need for that transformation did not emerge from engineering ambition alone. It emerged from industrial necessity. Factories needed resources. Railroads needed fuel. Cities needed steel. The entire system demanded more extraction than traditional methods could provide. And that demand was creating conditions for the arrival of machines so large, so powerful, and so destructive that they would permanently alter both the land and the people who worked upon it. The age of manual excavation was reaching its limit. Industry had encountered a problem too large for ordinary labor, and the solution that emerged would become one of the most extraordinary machines ever built. The giant excavating machines that eventually transformed American mining did not appear suddenly. They emerged from decades of industrial frustration. Every generation of engineers inherited the same problem. Industry demanded more material than existing extraction methods could reliably provide. Each technological advance solved part of the challenge. Then rising demand made that advance insufficient. The cycle repeated again and again. Steam power represented the first major breakthrough. By the mid-19th century, steam engines had already transformed transportation, manufacturing, and agriculture. It was only natural that engineers would attempt to apply the same principles to excavation. Early steam shovels proved that machines could replace large numbers of workers. A boiler generated steam. Steam-powered pistons. The pistons drove mechanical systems capable of lifting earth and rock. The concept worked. But success created a new problem. The more material industry consumed, the larger excavation projects became. Machines that once seemed enormous quickly appeared inadequate. Railroads played a crucial role in accelerating this transformation. No industry consumed resources on quite the same scale. A growing railroad network required iron and steel rails, timber ties, stone ballast, bridges, locomotives, maintenance facilities, and vast quantities of coal. Each expansion created additional demand for mining output. The railroad industry was effectively feeding a machine that demanded more raw material every year. Steel production intensified the pressure. The rise of large integrated steel mills dramatically increased ore consumption. Now, by the late 19th century, industrial companies were processing resources at rates that older mining systems struggled to match. The problem was no longer finding deposits. The problem was moving enough earth to reach them. Mining companies began investing heavily in mechanization. Initially, improvements focused on efficiency, larger shovels, more powerful steam engines, improved drilling equipment, better transportation systems within mines. But incremental improvements eventually encountered limits. Certain ore bodies required the removal of extraordinary quantities of overburden. Traditional machinery could not achieve the necessary scale economically. A new philosophy emerged. Instead of building slightly larger machines, engineers began imagining machines of unprecedented size. Whereas machines designed around volume rather than mobility. Machines intended to operate continuously for years. Machines whose productivity could justify their immense cost. The idea seemed extreme, yet the economics increasingly supported it. Consider the basic arithmetic. If a machine costing millions of dollars could replace hundreds or even thousands of workers while dramatically increasing production, the investment became rational. Industrial systems rarely reward moderation when demand is overwhelming. They reward scale. The 20th century provided exactly the conditions such machines required. Rapid urban growth, massive infrastructure expansion, rising energy consumption, military industrialization, all contributed to escalating demand for raw materials. These mining companies responded by pursuing larger deposits and developing more aggressive extraction methods. Nowhere was this trend more visible than in open-pit mining. Rather than following narrow underground veins, companies increasingly removed entire sections of landscape to expose valuable resources. Open-pit operations allowed greater production volume. They also required the movement of astonishing amounts of earth. The challenge no longer resembled mining in the traditional sense. It resembled industrial earth-moving on a geological scale. This environment encouraged the development of giant excavators. Engineers drew inspiration from earlier steam shovels, but expanded every aspect of the design. Larger booms, larger buckets, heavier structures, more powerful drive systems. Eventually, electricity replaced steam in many applications, allowing even greater scale and reliability. Electrical power changed the equation entirely. Steam systems carried limitations related to fuel transport, efficiency, and maintenance. Electric machines could operate continuously with fewer interruptions. They could deliver tremendous force through motors and gearing systems. Most importantly, they could grow larger, much larger. The result was a new generation of excavation machines whose dimensions approached the unbelievable. Some weighed thousands of tons, others exceeded 10,000. The largest became industrial landmarks visible from miles away. They towered above workers, above trucks, sometimes above nearby buildings. The 24,000-ton iron colossi belonged to this world, a world where engineering ambition merged with industrial necessity. These machines were not built because engineers wanted larger machines. They were built because the economic system demanded unprecedented extraction rates. Every component reflected that demand. Massive buckets capable of moving extraordinary volumes of material. Steel structures designed to withstand constant stress. Complex drive systems capable of operating around the clock. Electrical networks dedicated solely to powering the machine. Supporting infrastructure became almost as impressive as the excavators themselves. Rail lines transported material away from excavation sites. Workshops maintained critical components. Power systems supplied enormous amounts of electricity. Entire communities emerged around major mining operations. The machine became the center of an industrial ecosystem. This ecosystem extended far beyond the mine. Steel mills depended on ore deliveries, while power plants depended on fuel extraction. Manufacturers depended on both. The giant excavator sat near the beginning of a chain that extended throughout the industrial economy. Its importance was disproportionate to its visibility. Most people never saw these machines, yet many depended indirectly upon their output. This relationship reveals something important about industrial history. The most influential systems are often hidden from public view. Consumers see finished products. They rarely see the extraction networks that make those products possible. They see buildings, not quarries. They see electricity, not coal seams. They see railroads, not iron mines. The giant excavators occupied this hidden layer of industrial civilization. They were infrastructure for infrastructure. These machines built to supply the materials needed to build everything else. By the middle decades of the 20th century, their role had become indispensable. Entire mining operations were designed around them. Production forecasts assumed their performance. Economic plans depended upon their output. Industrial society had adapted itself to the capabilities of machines so large that earlier generations would have considered them impossible. Yet size alone did not make these machines extraordinary. Their true significance lay in how they worked. Because a machine weighing 24,000 tons presents challenges that exist nowhere else in engineering. The forces involved become immense, the movements deliberate, the risks amplified. And understanding those realities requires stepping onto the machine itself, into a world of steel, vibration, noise, and relentless mechanical appetite. The first thing you noticed was not the machine itself. It was the scale. Photographs rarely capture it accurately. Human eyes struggle to interpret objects that exceed familiar proportions. Standing near a 24,000-ton excavator felt less like approaching equipment and more like approaching architecture. The machine did not sit on the landscape. It dominated it. Steel towers rose above the excavation site. Massive booms extended outward like industrial limbs. Walkways, staircases, maintenance platforms, control rooms, and machinery decks stretched across distances normally associated with buildings. Workers did not simply operate the machine, they inhabited it. At full size, some giant excavators stood hundreds of feet tall. Their buckets alone could outweigh locomotives. Their structural frames contained thousands of tons of steel. Every component existed for one purpose: to move earth continuously. And continuous movement was the secret behind their power. Unlike explosive blasting, which released energy in sudden bursts, giant excavators relied on relentless repetition. Hour after hour, day after day, year after year. The machine consumed terrain through persistence. Electricity was usually the heart of the system. Massive electrical motors converted power into motion. These motors drove gear trains, winches, hoisting systems, swing mechanisms, and excavation equipment. The amount of electricity involved was enormous. Entire power distribution networks were often dedicated to supporting mining operations. Without constant energy, the machine became a motionless mountain of steel. With power, it became one of the most productive earth-moving systems ever created. The excavation cycle followed a carefully controlled rhythm. The bucket descended. Steel teeth bit into soil, rock, or overburden. Motors engaged. Cables tightened. The machine exerted tremendous force against the earth. Material broke loose. The bucket filled. Then the lifting sequence began. Thousands of pounds became hundreds of tons. The loaded bucket rose slowly through the air. The machine rotated. Material moved toward a dumping point. Then the bucket released its load. The cycle repeated. Again, and again, and again. The movements appeared slow, almost gentle, yet appearances were deceptive. A machine operating slowly can still move astonishing quantities of material when each motion involves hundreds of tons. Over the course of a single shift, these excavators could remove earth volumes that would have overwhelmed generations of manual laborers. The sound environment was unlike anything found in ordinary machinery. No single noise dominated. Instead, layers of mechanical activity merged into a continuous industrial atmosphere. Electric motors hummed with immense power. Gear systems groaned under load. Steel structures vibrated subtly as forces traveled through the frame. Cable drums rotated. Bearings turned. Metal contacted metal. The machine produced a deep mechanical presence rather than a single identifiable sound. Workers often described feeling the machine before hearing it. Vibrations traveled through platforms and walkways. Structural movements transmitted energy throughout the frame. Even routine operation generated a constant physical awareness of scale. The machine was always moving, always exerting force, always consuming material. Heat became another defining characteristic. Electric motors generated thermal loads. Gearboxes warmed under friction. Braking systems dissipated energy. Hydraulic systems, where used, operated under significant pressure. Maintenance crews monitored temperatures constantly because excessive heat could indicate developing failures. In machinery of this size, small problems rarely remained small. A damaged bearing could threaten production. A gearbox failure could halt excavation. A structural crack could require extensive repairs. Every component mattered because every component existed within an interconnected system. The bucket itself represented one of the most remarkable engineering achievements. Designed to survive continuous punishment, it had to withstand impact, abrasion, compression, and enormous loading forces. The teeth were often replaceable because rock gradually consumed them. Steel wore away, edges dulled, components fractured. The earth fought back against the machine constantly. Wear was inevitable. Maintenance therefore became inseparable from operation. Entire crews existed solely to keep the excavator functioning. Electricians inspected motors and control systems. Mechanics serviced gear trains and drive assemblies. Welders repaired worn structures. Lubrication teams ensured moving parts received continuous protection. Without maintenance, the machine would slowly destroy itself. This dependence reveals an important truth. The giant excavator was not one machine. It was a system. Operators, electricians, mechanics, welders, engineers, and support workers all formed part of its functioning. Remove any major element and production suffered. The machine appeared autonomous. In reality, it depended on constant human intervention. Movement itself posed extraordinary engineering challenges. How do you move 24,000 tons? The answer varied by design. Some giant excavators used rail systems, others employed walking mechanisms. The walking excavators were among the most astonishing machines ever built. Instead of rolling on wheels, they literally stepped across the landscape. Massive hydraulic or mechanical systems lifted portions of the machine and shifted its position incrementally. Each step required careful coordination. Each movement transferred enormous forces through the structure. Always watching one advance across a mining site felt surreal. A steel mountain was walking, slowly, deliberately, but undeniably moving. This mobility allowed the machine to follow expanding excavation zones. Where the ore lay, the machine went, and wherever it went, the landscape changed. Entire hills disappeared, valleys deepened, natural contours vanished beneath industrial geometry. What had once been terrain became material. This transformation was perhaps the machine's most important function. It converted geography into production. A mountain ceased being a mountain. It became overburden. A hillside ceased being scenery. It became a quantity to be removed. The machine's enormous appetite reflected the priorities of the industrial world that created it. Nothing was too large if it stood between industry and resources, and nothing was permanent if economic demand required its removal. Yet every cycle of excavation carried risks. Every moving cable, every rotating gear, every suspended load, every electrical system, every structural component. The larger the machine became, the larger the consequences of failure. And while engineers focused on productivity, the people who worked around these iron colossi understood something more immediate. A machine capable of moving mountains could just as easily destroy a human being. Because the same power that made these excavators indispensable also made them dangerous. And nowhere was that reality more visible than in the lives of the workers who operated them. For the public, the giant excavator was a symbol of industrial power. For the companies that owned it, it was an asset. For the engineers who designed it, it was a technical achievement. But for the workers who lived beside it every day, it was something far more personal. It was an environment, a world of steel platforms, vibrating walkways, electrical systems, moving cables, grinding gears, dust clouds, and constant noise. The machine did not simply perform work. It shaped the lives of everyone around it. Imagine arriving before dawn. The excavator already dominates the horizon. Floodlights illuminate sections of its immense frame. The steel structure emerges from darkness like a man-made cliff. You climb staircases and ladders that seem to continue forever. Wind moves through exposed platforms. Metal surfaces carry the memory of yesterday's heat and tomorrow's cold. Long before your shift begins, the machine reminds you of its scale. Once operations start, the environment changes. Motors awaken. Electrical systems engage. The structure begins to tremble, not violently, constantly. A subtle vibration travels through floors, railings, and machinery housings. Hours later, you no longer consciously notice it. Your body simply absorbs it. Day after day, year after year, noise becomes equally persistent. The machine rarely produces a single overwhelming sound. Instead, it creates a continuous industrial atmosphere. Motors humming, steel moving, gear systems turning, material crashing into buckets, rock sliding into spoil piles. The noise becomes part of existence. Workers learn to communicate through signals, procedures, and experience because ordinary conversation is often insufficient. Then, there is the dust. Every excavation operation generates it. Every bucket load releases it. Every dump cycle sends particles into the air. Fine mineral dust settles on equipment, clothing, tools, skin, and lungs. Maintenance crews fight it constantly. Workers breathe it constantly. Industrial history is filled with machines that seemed productive while quietly transferring costs into the bodies of those who operated them. The giant excavator was no exception, yet physical discomfort was only part of the burden. The real danger came from scale. Large machines create large consequences. A dropped tool can become a falling hazard. A damaged cable can release enormous stored energy. A structural failure can affect thousands of tons of moving equipment. Workers understood this instinctively. They respected the machine not because of its reputation, but because they lived inside its risk envelope. Every major excavator operation accumulated stories, near misses, equipment failures, unexpected collapses, mechanical incidents narrowly avoided through experience and luck. The machine's sheer size amplified every problem. A small bearing failure in ordinary equipment might inconvenience a crew. The same failure inside a giant excavator could halt production for days or weeks. Repair operations became major industrial projects of their own. Entire teams mobilized, replacement parts transported, specialized tools deployed. Downtime cost enormous sums of money. Pressure to restore operation quickly was often intense, and pressure has always been one of the hidden hazards of industrial work. Because when production schedules dominate decision-making, risk can become easier to accept. The machine's relationship with the landscape created another contradiction. It extracted valuable resources. It also consumed entire environments. Hills vanished. Forests disappeared. Natural drainage systems changed. Water tables shifted. Communities sometimes found themselves living beside landscapes transformed beyond recognition. The same machine that supported economic growth could permanently alter the places where that growth occurred. This contradiction became increasingly visible during the 20th century. As environmental awareness expanded, public attitudes toward large-scale extraction began to change. The giant excavator still represented productivity, but it also represented industrial appetite without obvious limits. Questions emerged. How much land should be removed? How much environmental disruption was acceptable? What happens after extraction ends? The machines themselves offered no answers. They were designed to excavate, not to judge. Eventually, technology began shifting again. The largest excavators remained impressive, but industrial systems became more diversified. Massive haul trucks improved transportation efficiency. Hydraulic excavators offered greater flexibility. Computerized planning improved mine design. Automation increased precision. New machinery often achieved similar results with lower operating costs and greater adaptability. The age of the giant iron Colossus began to fade. Some machines were dismantled. Others were abandoned. A few survived as industrial relics. Their enormous frames remained standing long after production ceased. Silent, rusting, immobile. The same machines that had once consumed mountains now struggled against corrosion and time. There is something haunting about these abandoned giants. Industrial civilization tends to celebrate innovation. It rarely contemplates obsolescence. Yet every machine eventually encounters it, no matter how large, no matter how powerful, no matter how successful. The excavator that once represented the future becomes a monument to a past way of solving problems. And still, their legacy remains everywhere. The steel in bridges, the stone in roads, the coal that powered factories, the raw materials that built cities. Many passed through landscapes shaped by these machines. Modern America was not built solely by inventors, financiers, or political leaders. It was built by extraction systems. And at the center of some of the largest stood machines weighing tens of thousands of tons, machines capable of altering geography itself. Yet perhaps the most important legacy is not mechanical. It is philosophical. These iron colossi revealed something fundamental about industrial society. When demand becomes great enough, even mountains can begin to look temporary. What previous generations accepted as permanent obstacles, industry learned to treat as material. The machines did not merely move earth. They changed the relationship between human ambition and the physical world. That transformation brought wealth, infrastructure, energy, and growth. It also brought environmental loss, worker exposure, and landscapes that would never fully recover. The giant excavators solved the problem they were built to solve. They fed the industrial hunger of a growing nation. But like so many industrial triumphs, their success concealed its own cost. Today, the mountains they removed are gone. The workers who operated them are largely forgotten. The machines themselves are disappearing. Yet the world they helped create remains all around us. Every railroad, factory, bridge, and city carries traces of their work. The iron Colossus ate mountains, and in doing so, it helped build America. The question left behind is whether the nation ever truly understood what it traded away in the process.